Welcome, everyone. Today's speaker is Will Bryan from University of North Carolina at Charlotte, and he'll talk about whether Omega star knows its right hand from its left. Please.
Well, thank you. And thank you for having me here. I do appreciate the opportunity. I haven't been able to make it to any of these meetings this semester because I normally teach a class starting in about half an hour, but today they're happy because we're starting class late and I'm here. So, oh, hold on. There we go. Okay, so I'm going to start by just reminding you of something you probably already know, but I'll remind you anyway. Compactification of omega. So by omega, I mean just the natural numbers with zero. So the set theoretic version of the natural numbers. And they're given this discrete topology. So whenever it's a topological space, it's just a countable discrete space. So there are many ways to compactify a countable discrete space. You can add a single point at an infinity, or you could add lots of points at infinity. Here, I've added closed interval at infinity, and you can have countably many points sort of converging onto that in some nice way. The Stone-Check compactification of omega is the space of all ultrafilters on omega, and it's the Stone space of the power set of omega, and it is the largest compactification of omega. So this is, in a formal sense, it's the largest compactification. You can compare two compactifications. There's a partial order, I suppose, not any two compare. But for example, you could say this compactification here on the right is larger than the one on the left, because I can go from the right-hand side to the left-hand side by taking all of the different points at infinity here and collapsing them down to a single point. And so the quotient of this space, by collapsing some of these blue points here, is going to be this space on the left. So it's bigger in a sense. It has more stuff at infinity. So the Stone-Check compactification has the maximal amount of stuff at infinity. So it's compactification where you can always find a way of collapsing some points at infinity that gives you any other compactification you like. Okay, another characterization of it, it's the unique compactification of omega. That has what's called the Stone extension property. So we have this nice triangle here. Omega is a subspace of beta omega. And if you give me any other compact Hausdorff space, X, and any sequence of points in X, so a way of just mapping omega into X, is essentially just a sequence of points in X, then I can extend that function, mapping omega into X. I can extend it to be well-defined on all of beta omega. You may have seen this before in the guise of these ultrafilter limits. So this function is sometimes denoted this way. So you take a limit along an ultrafilter of a sequence of points. Also, the thing that I said in the previous slide about it being the largest compactification, it follows from this property. So if you take any other compactification down here, that is a compact Hausdorff space, that's your X. Omega is a subspace of it, so you just take the identity map here, and the Stone extension property says that I can extend that identity map to a continuous surjection from beta omega onto gamma omega. So by collapsing points in beta omega, I get gamma omega, so it's the largest compactification. All right. If we take away the omega, then we get the Stone-Check remainder of omega. It's the Stone space of P omega mod fin. So take that Boolean algebra, mod out by the ideal of finite sets. And I want to talk about trivial mappings from omega star to omega star. So what a trivial mapping means is that there's some finite to one function on omega that induces this function on omega star via the Stone extension property. So if you look back at the diagram, the picture is something like this. So I have my finite to one function here, mapping omega onto omega, which is a subset of beta omega. I can extend it to a mapping from beta omega to beta omega. And if the function is finite to one, then it turns out that the points of omega star up here are just going to map to points of omega star down here. And so the function, the trivial self-mapping of omega star is just the restriction of this beta f that I have here. You can write down a formula for it. So look at an ultrafilter in omega star. That's just a non-principal ultrafilter on omega. And the function is just defined by looking at all the sets in the ultrafilter and taking their image under this finite to one function. Okay, why are these trivial? They're trivial because you can write them down and understand them. You don't need some complicated thing to tell you that they exist. They're just there and you can look at them and see them. So trivial in that sense. Here's an example of one. So the shift map on omega star is the trivial map where you take an ultrafilter and you just take every set in the ultrafilter and you shift it one unit to the right. So it's induced in the sense of previous slide. It's induced by the successor function that sends a number n to n plus 1. Its inverse is also a trivial self-homeomorphism. So this function, the successor function, isn't exactly invertible, but it's almost invertible, right? So I don't really have anywhere to put 0, but that's fine. I can just leave 0 put, subtract 1 from everywhere else. And this is mostly an inverse to the successor function. And because I'm working with p omega mod phin, or the stone tool of p omega mod phin, the mod and phin bit means that I don't really care about what happens at a single point here. So this is effectively, it's just as good as an actual inverse for this function here. And when I move to omega star, it is actually an inverse. So these are both homeomorphisms from omega star to itself, trivial homeomorphisms. Okay. Like I said on the previous slide, trivial in some sense means maps that you can see and understand. Are there any other maps? Was a good question that was asked a while ago. So the first answer to that question was given by Walter Rudin, and in a long time ago now, almost 70 years ago now, he proved that assuming the continuum hypothesis, you can build non-trivial self-homeomorphisms. You actually get, oh my goodness, this is a typo here. This is supposed to say there are 2 to the c self-homeomorphisms of omega star. And so that would, of course, imply that some of them are non-trivial, because I have up here that there are c many trivial self-maps. So anyway, sorry about that. There are 2 to the c self-homeomorphisms, assuming CH. And so in particular, there are loads of non-trivial ones. Most of them are non-trivial. But he needed the continuum hypothesis to do this. And much later, we found out, thanks to Schella, that he really did need the continuum hypothesis. There's no way in ZFC to construct a non-trivial self-homeomorphism of omega star. It's consistent that they're all trivial. This theorem kind of has a very rich history, or maybe history is not the right word. It began what now seems a very rich thread in set theoretic topology. So Schella's theorem was strengthened a few years later by Schella and Steprans. They showed that it follows from forcing axioms. So PFA implies that all self-homeomorphisms are trivial. Velichkovich weakened this to sort of just weaker forcing axioms, whatever that means. You don't really have to know. OCA plus MA is just weaker than PFA, the proper forcing axiom. And it's already enough to imply that all these things are trivial. And Ilias Farah, more recently, I think this was in his doctoral dissertation, actually, he proved that the same axiom, it doesn't actually just impose restrictions on the self-homeomorphisms of omega star. It's actually any continuous mappings from omega star to itself. If you're trying to work in ZFC, there are actually some very, very strong restrictions that you have. So in these models where forcing axioms hold, there's just not too much you can do to build non-trivial mappings from omega star to itself. You can have non-trivial mappings, but sort of only barely in some technical sense. Anyway, let me pivot a little bit and point out that what we've been talking about, we have this compact Hausdorff space, and we're talking about maps on this compact Hausdorff space. This is what's sometimes called a dynamical system. So you have a compact Hausdorff space and some self-homeomorphism of it. These are These form the objects of study in a very large field of mathematics, dynamical systems. In that category of dynamical systems, we have this notion of isomorphism. So one or two dynamical systems the same. So you want the underlying spaces to be homeomorphic, but more than that, you want the homeomorphism to sort of take the action of one of the maps and send it directly to the action of the other map. So there's a sense in which the mapping F on X is topologically indistinguishable from the mapping G on Y. So that's what it means for two dynamical systems to be essentially the same. You can weaken this. So this is, an isomorphism, the category of dynamical systems. You could talk about, just morphisms or epimorphisms. So if you're a dynamicist, you don't say epimorphism, you say factor map. So a factor map is something that looks like this, but the phi here, instead of assuming it's a homeomorphism, you just assume it's a continuous surjection. So you're sort of collapsing some points in X, getting some potentially smaller or simpler space Y. But again, you are sending the action of F to the action of G. Okay, so based on this slide and the previous slides, you might guess that I want to talk about dynamical systems where the underlying topological space is omega star. And you'd be right if you guessed that. So I want to talk about this question of Van Douwen. So we have two dynamical systems, omega star with the shift map and omega star with the inverse of the shift map. So remember from a previous slide, the shift map is the map that takes every ultrafilter and just scoots it to the right 1 unit in omega. And its inverse takes a non-principal ultrafilter and scoots to the left 1 unit. I guess it's important that I say non-principal, because if you have principal ultrafilters, that's not quite a homeomorphism anymore. But on omega star, when we're looking at non-principal ultrafilters, these are both homeomorphisms. And so we want to know whether there's any way to distinguish these two dynamical systems, or are they topologically the same? This is where I got the title of my talk from, right? So the shift map goes to the right, its inverse goes to the left, and can we tell the difference from a topological dynamical point of view? Well, okay, maybe we can, I guess, is Van Douwen's answer. So just to clear this up, by the way, for these dates. So Van Douwen died tragically early on in his life. So, well, he was young anyway. So he died in 1987. And he was a very, very prolific topologist, set theoretic topologist. And after he died, a lot of his friends organized his notes into papers and published these papers. And his papers that were published after he died filled 3 whole volumes of, I think it was topology and its applications, or it might have been topology proceedings, one of the two. So anyway, this work was published in that series of papers. So it was published in 1990, 3 years after his death. I think based on what's written there and people that I've talked to, he was thinking about this problem for at least a little while before he died. So I'm guessing around 1985. So this is an approximate date of when he might have been thinking about these things. It was published in 1990, but certainly he was done thinking about it by then because he passed away in 1987. Okay, so he proved that if these two dynamical systems are conjugate, then the conjugacy mapping, so the phi from the previous slide, is a non-trivial self-homeomorphism of omega star. So putting this together with the result of Shella, which says consistently there are no non-trivial self-homeomorphisms, this means that consistently the shift map and its inverse are not conjugate. So it's possible that there is a real topological difference between these two maps, scooting to the right by 1 and scooting to the left by 1. But also it's kind of an unsatisfying topological difference in the sense that we're not identifying any real topological property of the maps. One of them has this property, the other one has that property, and therefore they're different, right? It's more just there's something about the set theoretic universe we're living in that sort of prevents any conjugacy from happening, because the conjugacies would just have to be too terribly complicated, and we've somehow been able to prevent terribly complicated self-homeomorphisms of omega star from existing. Anyway, let me point out, actually, so I mentioned on a previous slide that Schella's work has been extended and generalized, and we can actually prove, using some of the work of Farah that I mentioned earlier, that not only assuming forcing axioms like OCA plus MA, not only is it true that you don't have a conjugacy between these two dynamical systems, it's actually consistent that you don't even have a semi-conjugacy or a factor map between these two systems. So you might not even be able to map omega star onto itself in such a way that the action of the shift goes to the action of the inverse shift, or vice versa. So consistently, these two maps, there's no topological connection between them at all. Okay, but this of course leaves open the question, what about the other way? Is this a ZFC theorem, just requiring a different proof, or is this the sort of thing that's independent of ZFC? And I worked on this question for a very, very long time, and eventually, recently, was able to find the answer. So the answer is that this is a thing that is independent of ZFC. So forcing axioms imply these dynamical systems are not conjugate, not even factors of each other, but the continuum hypothesis implies that they are conjugate. Okay. I should mention, especially since the title of my talk was about P omega mod phin and not omega star, I should mention that you can rephrase this in terms of Boolean algebras. So CH implies that if you look at the shift map on P omega mod phin, so that just means you take the equivalence class of some set and you shift the set to the right by one. This mapping is conjugate to its inverse in the automorphism group of P omega mod phin. That's assuming CH, assuming things like PFA or, even weaker force axioms like OCA plus MA, they're not conjugate, they don't even embed into each other, which is the stone rule of a factor mapping. So, okay, the proof of this is a bit long, and I'm not going to be able to sketch all of the ideas that go into it in this talk, but the goal for the rest of the talk is to sort of give an overview of part of the proof. So what I want to do is I want to sketch sort of the main ideas of the proof contingent on one big lemma. So I'll state what the lemma is, and I'll show you how to use the lemma in order to prove the theorem, but I won't get into how to prove the lemma. Proving the lemma is actually, that's kind of the hard part. But I'll at least state what the lemma is and then sort of show some of the ideas that go from getting from that point to a proof of the theorem. Okay. So the basic argument at its core, it's what's called a back and forth style argument. So probably you know what that is, but just to refresh your memory, I'll go ahead and say what that is. So the simplest back and forth style argument, even if you haven't heard it called that, it's certainly something you have seen before. So it's the kind of argument that you would use to show that any two countable dense subsets of the reals are order isomorphic. So suppose you have two countable dense subsets of the real line, and what you do is, okay, you stare at them for a second, and then you identify some point on the left set. So X on the left, Y on the right, identify some point on the left, and just pair it with some point on the right. So A0 pairs with B0. Then you take some point on the right, and you pair it with some point on the left. And the only thing you have to be careful about is that if B1 is to the left of B0, then you'd better make sure A1 is to the left of A0. But of course, if you have countable dense subsets of the reals, you can always do that sort of thing. Then you look at another point on the left, we'll call it A2, and you find some point on the right that you can match with it. On the left, we see A2 is to the right of A0 and A1, so that means our B2 should be to the right of B0 and B1. And okay, then I find a B3 on the right, and I find a matching pair on the left. So it's between B0 and B1. So I find an A3 that's between A0 and A1, and so on and so forth. The only other critical part of this argument, and this is where the countable bit comes in, is that the reason I'm doing this back and forth, so you'll notice I found A0 and then paired it with B0, so sort of going left to right. But then I found my B1 and paired it with an A1 going right to left. You want to go back and forth like this because the idea is that you can fix a well ordering of X and Y beforehand in order type omega. So finite segments are finite. Yeah, initial segments are finite. And then you can just, at any given stage, take your A sub n to be the next thing in your well ordering that hasn't been assigned a pair yet, that hasn't been matched with something on the other side yet, and vice versa. So doing it that way, everything gets matched up at some point, and we actually end up with an isomorphism at the end. So the argument here relies on these two facts. So fact number one is that the sets are countable, which really means that I can well order the sets so that all initial segments are finite. And the other thing it relies on is that when I have a finite partial isomorphism, say phi0, that brings maybe some finite subset of X to some finite subset of Y, some F to G. And then if I'm given some new point, this would be like my A sub n that I take at some stage of my construction, I'm giving some new point, I can find a mate for it over on the other side, right? I can extend my partial isomorphism phi0 to include that new point. Furthermore, I can do that not just going from left to right, but it works the same if I switch the roles of X and Y and want to go from right to left. So, okay, that's what the back and forth argument needs. All right, well, what are we going to do in our argument? In our argument, we want to do a similar thing, but our back and forth argument needs to be longer. So, oh, and I should have said this earlier, but let me say it now. When I sketch the proof, I'm going to talk about P omega mod phi rather than omega star. So I sort of told you what the theorem was in terms of omega star, and then told you what the stone dual says. When I sketch this part of the proof, I think I'd prefer to work in the stone dual. It just makes a bit more sense, I think, to talk about unions of Boolean algebras instead of talking about inverse limits of topological spaces. So we're going to do that. Okay. I want two things in order to make my back and forth argument work. Thing number one, I'd like to be able to well order the set P omega mod phi so that all initial segments of my well order are countable. Countable instead of finite because finite is too much to hope for. P omega mod phi is an uncountable set. So, okay, but maybe I can well order things so that all initial segments are countable. Then when I do, I'd like to have some kind of partial isomorphism extension thing like we did with the countable dense sets. So I'm given a partial isomorphism that takes some A comma sigma. So imagine A here is a subalgebra of P omega mod phi. So I'm looking at some small bit of P omega mod phi with the shift map. And I have a partial isomorphism on the some small bit of P omega mod phi with the inverse shift map. And these two bits are isomorphic, but they're only small bits. They're countable bits. I don't think I said A and B are supposed to be countable. I should have said that. So A and B are meant to be countable here. And what I'd like to be able to do is I'd like to be able to take some new thing, something that's not already in A, and I'd like to be able to extend my partial or isomorphism to put it in there. So I want to find an extension to a countable, still countable substructure of P omega mod phi that contains A and the new thing. Now, I don't want it to be just necessarily A plus the new thing. I might need to add some extra bits in there. Think about how the shift map moves things around. So if I add in X, I might also want to add in things like the shift of X and the nth shift of X for every X. I might also want to close up A prime under algebraic operations, meet and join and all those Boolean algebraic things. So A prime might be bigger than just A together with this new thing. But okay, I want to be able to extend my partial isomorphism to A plus this new thing. And I want to be able to do it both ways, not just with the shift on the left and the inverse on the right, but if you swap them, that should be fine too. So this is my wish list. The first thing on my wish list is equivalent to CH. So the cardinality of P omega mod phi is the continuum. And so I can order it in that kind of way if and only if the continuum has cardinality Aleph 1. So, all right, this is why I need CH to prove my theorem. Fine. What's the second thing on my list? Well, the second thing on the list is asking for this, we'll call it a lifting property for P omega mod phi with the shift or with the shift inverse, whichever way you want to look at it. But the idea is that I have this embedding, so subalgebra A, shift map here. Now, earlier I said a partial isomorphism. But that's all an embedding really is, right? So eta you can think of as just an embedding into this giant structure here. Equivalently, it's a partial isomorphism onto some substructure of that, okay? And then I also have an extension onto of A to some larger structure, A prime, that maybe contains some specified element that I'd like to extend my isomorphism to. And the question is, can I find an embedding here that makes this triangle commute? That's the question. If the answer is yes, then I can do a back and forth argument, just like on the previous slide, except that I need omega 1 steps instead of omega steps. So that's the dream. However, it doesn't work. So the second bullet point on the previous slide is not generally true. What I mean by that is that if you think of the solid arrows here as being like a question, does there exist a mapping here that makes it commute? There are questions where the answer is no, there doesn't exist something like that, and you cannot extend the mapping eta here to the larger substructure A prime. So sometimes this is impossible. Well, dang. Okay. So I was stuck at this point for a very, very long time. I realized, I think it was in around 2017, when I was working on this problem, that there were examples like this, structures where you have sort of bad extensions of A, or maybe bad embeddings of A. There are different ways to look at it. And there's just no way to complete the triangle and make things work. All right. So we have this transfinite recursion that we'd like to do, omega 1 steps, to do our back and forth argument. But at each stage, we're tasked. We have a job to do, right? We have this partial isomorphism, and we'd like to extend it to larger structures. And sometimes this task simply cannot be done. So we have undoable instances of this task that we need to do. So how do we get around that? The answer is that we need to do the transfinite recursion very carefully. And if we're careful enough, we can make it through all omega 1 steps of the recursion while avoiding ever running into any undoable instances of this task, this problem of lifting isomorphisms. Okay, so what does that mean? Well, here's the lemma. This is the key lemma that I told you I was going to state it, and I wasn't going to prove it. Okay, here it is. So this lemma essentially says that if your question is well-behaved enough, then yes, there is always an answer. So it's a way of avoiding these undoable tasks, these undoable extension of partial isomorphism problems. So what exactly does it say? All right, so we're given these countable structures of the shift map. We have A, we have A prime. A prime is bigger than A, so I have this inclusion map from A to A prime. All right. And I also have a way of embedding A into P omega mod phi with the shift inverse. So I'm going from the shift side to the shift inverse side. Imagine I want to do a back and forth argument. So I'm going from one side to the other. And like I said, if that's all that I know, then maybe there is no extension of the embedding. Maybe I can't find an eta bar that works like this. So what we want to assume here is that this embedding eta is elementary. Now, this is in quotes. It's not exactly an elementary embedding, or actually, it turns out that it is, but you can only prove that much later down the road of working on these things. But what I mean is it's kind of related to elementarity anyway. What I mean by this precisely, for the moment, is that when I look at the image of eta over here in this structure, then what I'm seeing is an elementary substructure. So precisely here, the image of the structure A under eta, when paired with the shift inverse mapping, is going to be an elementary substructure of P omega mod phi with the shift inverse. Okay, so that's the lemma. Like I said, I'm not going to try to prove it, but there it is. So what I want to do now is I want to show how with this lemma, we can, this lemma is enough to enable us to do the back and forth argument that we need to do in order to prove the theorem. Okay, so that's what the next few slides are going to look at. So step one, we're going to use CH right out of the gate. Let's just, at the very beginning, we're going to fix a well order of P omega mod phi in order type omega 1. So y omega 1, that means that all of the initial segments of this order type are countable. Okay, done. Step 2. Let's prove this is sort of a second lemma after the main lemma. So I showed you the main lemma on the previous slide, and it's important to know for what we're about to do, the back and forth argument, that it actually works in either direction. If we go back at this here, if you look at this picture here, I have sigmas on the left, shift map on the left, inverse shift map over here on the right. If I completely swap that around, and I had two substructures of the inverse shift over here, and then just the shift over here, then that's fine too. It's actually, I'm not going to go through why this is true, but let me just point out that you can get that sort of reversed version of the lemma. You can get that fairly easily from the lemma. You don't have to sort of prove it twice, changing things here and there and redo the proof with everything swapped around. You can actually deduce it as a corollary to this lemma pretty quickly. So, okay. We have this lemma and we have a reverse version of the lemma as well. Fine. Step 3. We're going to begin the recursion. So we have this transfinite back and forth argument. Here's step 1, or well, okay, step 3, fine. But step 0, I guess, of the recursion, if we think of it as the base step of this omega 1 length recursion. So what I'm going to do to begin my recursion here is I'm just going to fix a countable elementary substructure of the thing on the left-hand side. So I've put P omega mod fin with the shift map on the left, shift inverse on the right, and I'm starting down here with this nice elementary substructure. So how do you know a substructure is elementary in my pictures? You're going to know because they're the ones that have these nice smooth boundaries here. So that's meant to denote elementarity. Okay, next step. Embed this structure onto the right-hand side. Now, there's a hidden lemma here that I haven't proved for you, so you just have to take my word for it. But actually, P omega mod fin with the shift and P omega mod fin with the shift inverse have an identical set of countable substructures. So a countable, let's say, well, how do I put this? Well, maybe I'll put it this way. If I have a substructure over here on the left-hand side, it is also somehow a substructure on the right-hand side. And if I have any countable substructure on the right-hand side, it is also up to isomorphism, a countable substructure of the left-hand side. So up to isomorphism, they have the same countable substructures. So I know that there's a mapping from here to here. But when I prove that lemma and I build that mapping, what I don't have control over is the image of the mapping. So I know that there's a way to embed this nice structure here over here, but what I don't know is whether I can make the image elementary. So this is why this is not a nice blue oval. This is a jagged red thing. We have no way to guarantee that the image of the embedding is elementary. So, okay, I'm mapping, I think of it as a pretty side and an ugly side to my back and forth argument. So currently the left side is the pretty side, and I map things to the right, and now things look ugly. Okay, step 5. Watch the picture. I'll go back. So step 4, it looks like this. Step 5, all I'm doing is flipping the arrow over. So an embedding is a partial isomorphism, right? So there's an isomorphism between the nice blue thing and the ugly red thing. So we're just going to view that isomorphism as moving in the other direction. The red thing is isomorphic to the blue thing, rather than the blue thing to the red thing. Okay, it's not a huge distinction, but it's kind of powerful. Why? Because what I can do now is, thanks to Lowenheim Skolem, I can find a countable elementary substructure of P omega mod fin shift inverse that covers the ugly countable structure that I started with. So now what do I have? I'm in this situation. I have an ugly countable structure here, and I have this nice looking superstructure of it, still countable. This is nice looking because it's elementary in the big thing. And the ugly thing is mapping over here to this pretty substructure. So what we have here, in other words, is exactly the sort of situation where our lemma applies. The red thing, the ugly thing, is my A. The pretty thing is my A prime. So that's sort of the left-hand side of the triangle, if you think of that commutative triangle that we had for our lemma. And then the image of the red thing under this is like the eta in our lemma, the image of the red thing under eta is pretty. It's elementary in P omega mod fin with the shift. That was the hypothesis that our lemma needed. So we have a pretty image of the small thing. That means, by the lemma, I can extend the mapping to the big thing. Now, when I extend it, I again have no power to guarantee that the image of the extension is elementary. So we get an ugly red polygon on the left-hand side that covers my nice, pretty oval that I used to have. Okay, but once again, I can turn the arrow around. I can cover my ugly polygon with a pretty countable elementary substructure of P omega mod fin with the shift map. And then I can say again, aha, this is the kind of situation where my lemma applies, right? So I have, this is like my A, the ugly structure hidden in here. My A prime is the pretty structure that contains it. And this is like my eta in the triangle. So I'm mapping over to this thing, and the image of A is elementary in P omega mod fin with the shift inverse. So that means, once again, I can extend the mapping to the larger structure. That's one stage of the back and forth argument. So just reviewing that, what were we able to do? Well, okay, at any given stage, on the left-hand side, at some point, I said, we can extend this ugly guy to a countable elementary substructure of this thing that contains it. When I make that extension, I have the power to toss in any particular element of P omega mod fin that I like, anything I want. I have the power to put it into that pretty structure there. Same deal on the right-hand side. When I moved from this ugly red polygon on the very inside here, when I extended that to this pretty ellipse here, I was able to toss in any member of P omega mod fin that I liked. This is how Lowenheim-Skolem works. So, there it is. So what I need to do, essentially, remember I have this well-ordering of P omega mod fin that I fixed at the start? Just at stage alpha of this recursion, all we need to do is make sure that we put the alpha-ith member of P omega mod fin into our partial isomorphisms that we're building, do that on both sides, so that by the end, every member of P omega mod fin gets into these structures that we have these partial isomorphisms between. That way, at the very end, after omega 1 steps, we have a full isomorphism between the structures. Now, because this is transfinite recursion, building these partial isomorphisms, not regular recursion anymore, it's omega 1 steps. We need to do something at limit stages, but it turns out that's actually pretty easy. So at limit stages, just take unions of stuff, right? We take a union of these things that we're building on the left, these increasing structures on the left, take a union of these increasing structures on the right. Because all of the maps that we're building are just extensions of each other, when we take unions on the left and right-hand side, the maps cohere, and we get a map between the left-hand side and the right-hand side. And because all of our maps are partial isomorphisms, and that's a finitary property, we get a partial isomorphism between the union of the left-hand bits and the union of the right-hand bits. So at limit stages, we really don't have any problems with this recursion. The hard bit is just at the successor stages, how to lift these maps. And that's precisely what the lemma does for us. Okay. So that is the sketch of the back and forth argument and how the lemma enables us to do the back and forth argument. All right. Where did I use CH in this argument? The answer is that we only needed CH in order to make sure that as we were building these partial isomorphisms, after omega 1 steps, we could actually have everything, right? We could have all of P omega mod fin on the left and all of P omega mod fin on the right and an isomorphism between them. Even if we don't have CH, though, we can still use our lemma. That lemma didn't assume CH. We can still use our lemma to sort of do this recursion as best we can. And what you'll notice is that after omega stages of the proof, remember I said we take these unions. Well, the union of these increasing structures on the left and right are going to be elementary in their respective, P omega mod fin with the shift and P omega mod fin with the shift inverse. Because the elementary substructures, the nice substructures, are cofinal in this union. So what we get after omega stages the proof, whether CH holds or not, is an isomorphism between elementary substructures of this and this. So one corollary to the proof is that these two structures are elementarily equivalent, whether or not they're isomorphic. So this is true even assuming, in models like PFA, where we know they're not isomorphic, they're still elementarily equivalent. So kind of bolstering that theory, that mindset, I suppose, I think I mentioned it earlier, that under PFA or OCA plus MA, under those forcing axioms, there seems to be no real difference between the shift map and its inverse. There's no real definable topological pinpointable thing where you can say, this is how they're different. There's just no real way to map them onto each other. I feel like this, I don't know, to some extent confirms that in my mind. Okay, another corollary, and this is, I'm not claiming it's easy to see based on the sketch that I've given today, but it's another thing that you can prove using that main lemma. So another thing that you can prove using that main lemma that I showed you earlier is this, which is that there's a non-trivial way to send the shift map to itself. So one question that I heard about, I think it was 5 years ago, that I heard at a conference was just whether or not there's any way to do this. Can you conjugate the shift map with itself other than by using some power of the shift map? The answer turns out to be yes under CH. Ooh, that's an oversight. This is under CH. Of course, I already mentioned it's consistent. There are no non-trivial self-homeomorphisms. So certainly this can't be true always. This is true assuming CH. Okay. Assuming CH, the answer is yes. There's a non-trivial self-homeomorphism from omega star to itself. In fact, there are at least continuum many non-trivial self-homeomorphisms. So, lots and lots other than just powers of the shift map itself. I suspect there are two to the continuum many, but I haven't worked that out yet. Okay, and that's all I really have to share. I'm going to end with this question, which is a question that is related, I suppose, or at least it feels related to me. It has to do with reversing the order of something that's a stone check remainder. So just to explain what's going on here, this is the right half of the real line. So it's the ray beginning at the origin and going out to infinity. I want to take the stone check remainder of that ray. Now, when you do this, the stone check remainder of the half line, you get this really fascinating structure. It's a continuum, so a connected compact Hausdorff space. You get this continuum that is very, very, very intricate. It's a very, it has lots of universal properties, an immense amount of structure. There are all sorts of theorems about it. It's just a really, really cool thing to study. But anyway, there's kind of a natural way of looking at these, they're called standard subcontinua of this giant thing here. And those have a natural ordering on them that it inherits from the ordering on the ray here, from 0 to infinity. And what's not known is whether there's necessarily a way of reversing that order. So finding a self-homeomorphism of this gigantic continuum that somehow swaps everything around and turns forwards into backwards. So in other words, I guess the question is, does the stone check remainder of the half line know its right hand from its left? The answer is, I don't know yet. Consistently, the answer is no. This once again follows from forcing axioms like PFA. This is later than the work of Schella and Steprins and Velichkovich and Farah that I mentioned earlier. It's actually a pretty recent theorem of a guy named Alessandro Vignati. But anyway, the answer is no under forcing axioms. So again, it seems somehow connected to these maps on omega star. But anyway, that's a question that I would like to extend some of this stuff to, and that's where I'm going to end.
Thank you.